Today we'll be looking at a beta decay question. So the first part of the question asks us to estimate the radius of the nucleus. To do this, we use this equation, quite simple, and this yields an answer of 4.7 femtometers. R0 is usually 1.2 femtometers. Check with your lecturer to find out which is the correct one to use. Part 2 asks us to calculate the maximum momentum of the beta particles. Here we use this equation, where m is the rest mass, so it could also be denoted m0. The total energy is denoted by the energy conservation equation, E equals T plus mc squared, where T is the kinetic energy, and m is also the rest mass. Here we are using the relative regime. To deduce whether or not in a situation you must use the relative regime, you must look at this condition and whether or not it is satisfied. If it is satisfied, then you're working in the classical, and T equals p squared over 2m as usual. But in this case, T is 0.7 megaelectron volts, and mc squared is of course 0.511 megaelectron volts. The next step is to put in our numbers into the energy conservation equation. This gives us E equals 1.211 megaelectron volts. And then we replace this E into our original equation, and then solve for P, like so. To convert into SI units, we times by 1.6 times 10 to the minus 13 divided by 3 times 10 to the 8. The final part of this question asks us to calculate the angular momentum. You may recall this equation, L equals R cross P. To calculate the maximum angular momentum, we'll be looking at when sine theta equals 1. So the magnitude of L equals R times by P. Place in our numbers and we get a value of 0.026 h bar. But for the minimum quantum unit to be imparted, L must satisfy this condition, where L equals 1 being the minimum angular momentum imparted. But in this case, it does not satisfy this equation. So classically, we don't expect any angular momentum to be imparted. Decays that obey this condition are called allowed decays.